These are the solutions to the gravitational potential questions. So as I mentioned in the tutorial, these can cause a lot of problems in the exam in terms of the language used, and the formula can be quite tricky. And there's usually a lot of information in the questions. So we're told there's a mass of the satellite. We're told the height. We should be looking at kilometers. That needs to be into meters. And then we've also got the radius of the Earth, so the total distance. We need to add those two together. So the first thing, part A, says find the gravitational potential at this orbital height. Now, very often in the exam, students just don't know what to do with this at all. So you must be able to find, or even better know, but certainly find the correct formula. So this is the one we've learned. So V, so it's not voltage, V is gravitational potential in this context, is equal to minus, that's important, GMR. So if we can find that, then it is a straightforward calculation. It's just a simple substitution. We know G, we're given the mass. Hopefully we'll be given that. And we, very importantly, two things here with the radius. So it's the distance from the center of the Earth to the satellite. So we need to add together the height above the Earth's surface with the radius, both in meters, so times by 1,000. And then we get this big number here. Make sure you've got the units. So we know the definition of gravitational potential is the work done per unit mass. So that's joules per kilogram. And the negative sign is important. So we said earlier on in this topic, sometimes we don't need to worry about the negative sign if we're looking at the force, but with the gravitational potential, it is really important. Part B should be basically the same, a little bit easier actually, because we just have to do the same calculation, but now just with the radius of the Earth. So everything should be the same, but rather than the height, we just have the radius times by 10 to the 3 as before. And once again, we've got joules per kilogram. We've got a negative. So we should expect a larger value here because we're dividing by a smaller number. The change in potential, so the change in gravitational potential, is the difference between these two. So we could do this mathematically. So it's the final, take away the initial. So we've got minus, minus. Or if you prefer, we could just ignore the negative signs and work out the magnitude of the difference between the two. So that's the larger one, take away the smaller one. That would give us the correct value. So sometimes students find that easier just to forget about the negative numbers and just work out the magnitude of the difference between the two. So that's our delta V. That's our difference in gravitational potential. And to work out part D, the change in potential energy, once again, we have to go back to the definition of gravitational potential, which is the work done per unit mass, or the energy per unit mass. So all we need to do here is to multiply delta V, which we found already, by the mass of the object, not the mass of the planet. So that's a straightforward calculation, and we should expect to get a really big number. Remember that 1 joule is a very, very small unit of energy. So if we're moving a very large satellite into orbit, then we should expect a huge value for energy. Question 2, this is a really typical question. It looks quite complicated, this idea of equipotential lines. I think very often if students have missed this lesson, or have not understood it, or forgotten about it, it sounds like something very, very complicated, but it's actually very, very straightforward. So equipotential lines is a line. Remember, this is a 2D representation of a 3-dimensional situation. So it's a space or an area, the shell of a sphere, where all the potential, the gravitational potential, is the same. So we're told A is 40 or minus 40. We've got this negative. So which are the correct potentials for B, C, and D? So A and B are on the same line here. Equi means the same, so that means they must be the same. C is closer to the planet, so we'd expect that to be a larger negative value. And D is further away from the planet, so we'd expect that to be a smaller negative value. So there are no calculations required here. All we need to do is to understand what do we mean by equipotential line and how do these lines relate to each other. So the closer we get to the planet, the larger the negative value, and the further away we get, the smaller the negative value, until at some point, by definition, we get to an infinite distance. It's not really infinite. It's deep space where the value of gravitational potential is actually 0. So we're increasing the value in a negative sense to get to 0. Question 3 is difficult. This was a version of an exam question that came up a few years ago. A lot of students really struggle with this. They didn't know where to start with it at all. It is quite tricky. It's worthwhile thinking about, especially thinking about eclipses and the like, which we had in 2026 fairly recently, a few weeks ago from the point of recording. This is a real position. This happens. The moon moves between the sun and the earth, and we might get a solar eclipse. So this is, we need to think about what's happening in terms of the forces, what's happening in terms of the gravity. So the moon is between the sun and the earth, so we have an attractive force between the sun and the moon, pulling it to the left. We have an attractive force between the earth and the moon, pulling it to the right. So what is part A, the resultant field strength? So we're trying to find little g. So we need to say, well, what is the formula for little g? Once again, you're not expected to know these, but you are expected to be able to locate them in the formula booklet. And that can be tricky depending on, well, certainly with Educast, which is the exam board that I teach currently, it can be quite hard to find, but it's gm over r squared. So it's inverse square, but we only have one of the m's, one of the masses. That's the big M, the big mass. So it's the mass of the Earth, the mass of the sun, and it's going to be the difference between the two. So it's one take away the other. So we don't know which is the biggest. We could assume the Earth is larger in terms of its value of g, or the sun is bigger. But we're just assuming that Earth is positive and the sun is negative. But they are acting in different directions. So the g values do not add up together. They're trying to cancel each other out. But once we have this, then it should be a case of simple substitution. We know g in both cases. We're given that in the formula booklet. We're given the mass of the Earth. We're given the mass of the sun, which is much bigger. And we're given the distances. Don't forget that that's squared. I think we're told these in meters, so that's fine. We don't need to convert from kilometers to meters, but we do need to square it. So this is an example of identifying the right formula, substituting correctly, and then good calculator technique. So a lot of students would have got this wrong, I think, in the actual exam, because they just got a bit confused with all the numbers. But if you do it this way, then with the Earth take away the sun, we get a negative value here. So it's really small. It's approaching 0, so it's a lot less than 9.81, certainly. If it's negative, then that would be towards the Earth, or perhaps it makes more sense to say that it's positive towards the sun. So the sun is dominant, so we have gravitational field strength in this direction, effectively. So we need to consider that direction. Gravitational potential, same idea. Watch out for the formula. So it's basically the same calculation, but rather than divide by r squared, now we're going to divide just by r. So all the numbers are the same. So we've got g, we've got the mass of the Earth, we've got the mass of the sun, and now we've got the distance between Earth and the moon, but not squared, and similarly between the sun and the moon, not squared. So we get a very different value for v joules per kilogram, and this would come out negative the way we've calculated it here. So a difficult question, quite abstract, lots of calculations, lots of calculator techniques required, but you should be able to do this, and you certainly need to practice this because this type of question does come up in the exam. The final two questions are things that again, very often typical exam questions. We need to show that the units of, in this case, gravitational potential are joules per kilogram. So that's something we need to do. And we might be asked to derive this formula. So you may or may not be given this, depending on which exam board you're doing. But this is definitely something which is worth deriving. So let's think about the units. So we always start off with the formula. So we're trying to find gravitational potential. V is equal to minus gm over r. So the big G, we're given that in the formula booklet. We're told that's newtons meters squared kg to the minus 2. The mass is obviously kilograms, and r, the distance, is meters. So we can tidy this up a little bit. We've got kilograms to the minus 2, so that just gives us kilograms to the minus 1. We've got meters squared divided by meters, which gives us meters. So Newton meters per kilogram. is how we could write the units of V. And work done is force times distance. This is a really, really useful definition. It's a really useful formula. I tell my students this crops up all the way through year 1 and year 2, and very often students forget that totally. So work done is a form of energy or energy transfer. F times D, well, F times D is newtons times by meters, Newton meters, and work done is basically energy, so we have joules. So Newton meters here, Newton meters is joules, joules per kilogram. So by looking at all the units and understanding where Newton meters, how that's related to work done, we can show that the units are joules per kilogram. And final question, this derivation here, so let's have a look. We know that we have lots of kinetic energy if we're launching a satellite, and we assume that all of that is converted into GPE. So we can say, well, half mv squared, that's straightforward. We've got to be careful because at GCSE, we would just say this is mgh. But the important thing here is that g is changing over this large distance. It's not just a distance of 1 or 2 meters, which is fine for GCSE. So we need to go back once again to the definition of gravitational potential. So it's the work done per unit mass. So if I know the gravitational potential, which is our formula G/m/r, and I multiply by mass, then that will give me the work done, which is the energy, and that will be gravitational potential energy. And we should be able to tidy this up a little bit. So get rid of the little m. So little m cancels, and we just rearrange this to make v the subject, and we get root 2 G/m/r. And that is our derivation. So that could be worth 2 marks, possibly 3, if you're asked to maybe explain the significance of it. But it is a really useful formula. All we need to do is to know big G, the mass of the planet, and the height or the orbital height that we're trying to get to. We do not need to know the mass of the object that is being put into orbit, or well, it wouldn't be orbit, it would be into space, because little m cancels.